For part 3 of chapter 17, we're going to pick right back up with where we left off in the Aldol addition, specifically a crossed Aldol addition, where we saw that with two possible enolates and two possible carbonyls, right, we left off with four products that reaction would produce, right? So it would be terrible for synthetic utility. You could never hope for more than 25%. But if we're designing a crossed aldol addition for synthetic applications, okay, we can preferentially, well, not preferentially, you'll do it if you're doing this next reaction. All right, make sure that one of the carbonyls that you're working with, the aldehyde or the ketone, doesn't have any alpha hydrogens. Okay? Because if you don't have alpha hydrogens on your carbonyl, you can't deprotonate it to form an enolate ion. So that cuts your possible products down from 4 to 2. Okay? And that type of reaction, a crossed aldol addition, where one of your carbonyls does not have alpha hydrogens, is called a Claisen-Schmidt condensation, another named reaction. Yeah. And the order that you add these things is important. Notice it's a two-step reaction, right? We start with benzaldehyde here in a solution with hydroxide, and then we add in our carbonyl that has the alpha hydrogens slowly. Okay, so we add the thing that has the alpha hydrogens to the thing that doesn't have them. Okay. And that order is important because when you put the thing in that has the alpha hydrogen, it'll get deprotonated to form an enolate, and then it's a game of probability. It's going to react with the thing that's higher in concentration, which is the other reactant that doesn't have the alpha hydrogen. So here we're maximizing our yield of our desired product. Okay. And the other thing to look out for in the Claisen-Schmidt condensation is that you immediately lose water. We talked about this in the previous video to form a conjugated product, hence why it's called a condensation reaction. Okay, that'll happen immediately because it's stabilized by conjugation. Okay. Now, if one of your products, or sorry, your thing that would take two, if you have to have alpha hydrogens on both of your carbonyls, there's no way around it. You first use LDA, which we used in the previous video as well, to deprotonate the alpha hydrogen. Okay, then you add your other reactant in slowly. Okay. It's again a game of probability, so you have to do it stepwise. But you'll never get as good of a synthetic yield using this procedure as you would if one of your reactants didn't have an alpha hydrogen to begin with. Okay. So with that in mind, video 2 and what we just talked about here, right, we can easily do a retrosynthesis to determine the starting materials. Okay. If you see a beta hydroxy ketone or beta hydroxy aldehyde, right, you just cut this bond here between the alpha and the beta carbon. Okay. That's what was formed by your aldol addition, so use that to figure out the materials that you started with. Okay. Then do your synthesis. Here, because both of these have alpha hydrogens, right, LDA would be needed to deprotonate. The other gets added in slowly, and then we hydrolyze to our final product. You can do it here, seeing a beta hydroxy ketone, or if you see the alpha beta unsaturated aldehyde or ketone, you again would break the same bond. It's just that extra condensation step that was shown right here. Don't let that throw you off. So that brings us to 17.13, okay, the Claisen condensation, which, okay, first thing you're thinking, didn't we just say that? What we were looking at before was the Claisen-Schmidt condensation. This is now just the Claisen condensation. And the difference is that it's still a condensation reaction, but it's specific to using two molecules of an ester. Okay, so previously we were looking at aldehydes and ketones. Now we're looking at esters, just Claisen, just esters. So here we see two equivalents of an ester. Okay. And our product of the Claisen condensation is a beta keto ester. And this happens via a nucleophilic acyl substitution reaction, which is why we're specific to esters, right? Because now we have a leaving group. The molecule, it's a condensation reaction, and the molecule we're removing here is now an alcohol instead of water before. And the other thing to pay attention to, right, is the base that you use is the same as your leaving group on your ester. Why is that? Okay. If our base happens to attack our carbonyl, well, no big deal. Doesn't matter who leaves, we regenerate it. Okay, because we've got a competing reaction. We'll compete with what's shown here, attacking the carbonyl and deprotonating an alpha hydrogen. It's competition. You're naturally going to get some of this. There's no way to prevent it. But you can prevent it from forming a new product by making sure your base is the same as your leaving group. Once you've made sure that is the case, right, what's the mechanism look like? Well, it looks like everything else we've seen. Deprotonate the alpha hydrogen, okay, create your enolate ion. That enolate ion adds to the carbonyl carbon of your second ester, forms a tetrahedral intermediate. Just like we've seen for several chapters now, that tetrahedral intermediate collapses, our leaving group leaves, okay, reform the pi bond, and we have formed, right, our product. That's simple. So how does that compare to the Aldol addition? Okay, well, our Claisen condensation, right, as we just saw, reforms the pi bond and kicks off the alkoxide leaving group. Whereas an Aldol addition doesn't have a leaving group, so it picks up a hydrogen, right, which is why you always see water in the last step, to produce a beta hydroxyaldehyde or ketone. Whereas here, now we're producing a beta keto ester. So that's the difference between the Claisen condensation and the Aldol addition, and the Claisen-Schmidt would be a subset of the Aldol addition. And the difference is because the ester has a leaving group that can be eliminated. Okay. If we want to get good synthetic yield using the Claisen condensation, okay, not only do we need to make sure that the base is the same as the leaving group of the ester, notice this is a reversible reaction here, right? And it actually favors the reactants. So in order to drive this reaction forward, you actually want to have an ester that has 2 alpha hydrogens, because this step, the deprotonation, notice is just a forward reaction. Okay, so I can deprotonate the beta keto ester, and then this lone pair is delocalized onto 2 different groups. We talked about that in the first video, right? And that drives the reaction forward. If you only have 1 alpha hydrogen, it's going to keep going back to the reactants. Here we've got Le Chatelier's principle, and while the left-hand side is favored, if I'm removing this from solution by turning it into the beta keto ester anion, this solution or this concentration is going down, so it's driving my reaction forward overall. Okay. So I'm going to look now just at a summary of the condensation reactions. Note I am skipping some slides from the end of 17.13, which discusses crossed Claisen condensations. I'm going to omit those for our coverage of chapter 17. Okay, effectively what it is just more of what we've seen. Okay? We're just looking at alpha hydrogens. If ideally you don't want one of your reactants to have any alpha hydrogens. That makes everything simpler. If they do, you have to use LDA to make your enolate. Okay, and then add the other thing in slowly. That's simple, but the order is important. The other thing we need to consider is intramolecular condensation reactions, and that also has a special name called a Dieckmann condensation. Okay. Effectively, what a Dieckmann condensation is the Claisen condensation, but it's specific to being an intramolecular reaction, and it will only work to form a 5 or a 6-membered ring. Okay. We've talked about that for 2 semesters now. Those are the most stable rings that we can form. Okay. But other than that, everything's the same. Okay. Base is the leaving group from your ester. You have to start with a diester for a Dieckmann condensation. Okay. Then you hydrolyze it, form your beta keto ester. 5-member or 6-membered rings only. So here, right, we see a 1,7 diester. We form a 6-membered ring. You may run into situations, right? Well, here we'll talk about the mechanism, but you may run into situations where you've got different alpha hydrogens to deprotonate, and you always have to think about the ring that you're making, because the mechanism is the same as everything we've considered before, right? Base deprotonate the alpha hydrogen. Now the alpha hydrogen, or the carbon ion, attacks the carbonyl. Okay, kick off our leaving group, bam, we form our product, right? But what about what we're making? Okay, if I have a 1,4 diketone, I have 2 alpha hydrogens I could pull off, right? I could pull them off from the inside, I could pull them off from the outside. But one of those is going to make a 3-membered ring. The other one is going to make a 5-membered ring. And you're always only ever going to form 5-membered or 6-membered rings via Dieckmann condensation. Okay. Same thing over here, right? Could form a 5-membered ring or a 7-membered ring. You're only going to form the 5-membered ring. Okay. And here we have 2 more possibilities, right? 1,5 diketone, 1,7 diketone. Both of those are going to preferentially form 6-membered rings. Okay. So Claisen-Schmidt condensation, Claisen condensation, and Dieckmann condensation. We have one more named reaction from this chapter, which is known as the Robinson annulation. Okay. What the Robinson annulation does is take our Michael reaction and our Aldol addition together to make an unsaturated cyclic ketone, specifically an alpha beta unsaturated cyclic ketone. And it's a famous reaction because it's ring forming, and that has really useful synthetic applications. We've talked about the challenge of forming carbon-carbon bonds, but forming carbon-carbon bonds and a ring, right, has its own useful niche. So what does the Robinson annulation look like? Okay, well, the first stage is my Michael reaction, okay, to form a 1,5 diketone. Okay, then after that, stage 2, I'm doing an intramolecular aldol addition. And then I heat it in basic solution to do a dehydration, and that is my product. Okay, everything else will vary based on your reactants, but the Robinson annulation always has 2-cyclohexanone, right, which is right here. Cyclohexanone, ketone starting at the 2 position, 2-cyclohexanone. So if you see that, that's kind of a clue that you're dealing with the Robinson annulation. And you can look for that when you're doing a retrosynthetic analysis. Super simple, because you've always got that part of the molecule to look for. Just draw a line between the pi bond and between the beta and gamma carbons up here. Just draw that straight line down, boom, cut it in half. Those are the products that you started with. You've got to have an alpha beta unsaturated carbonyl, diketone, you're in business. Easy to figure out what made it. So 4 named reactions to look out for, right? Probably the hardest hitting video from Organic 2 in terms of named reactions. Be familiar with the products that they form, right? They're all related, similar mechanisms to one another, just slight differences between the 4.